So in this video, we'll be looking at example 10 from the note packet. This is another free fall example. So in the problem, it states that there's a skyscraper in New England that's 790 feet tall. One of the problems with this skyscraper is that some of its windows that are 500 pounds become dislodged and then they fall to the ground. So the problem is asking us to determine the time that it takes for the window to fall from 370 feet and then the speed of the window before hitting the ground. One of the things it says is that we can assume that the window is in free fall. That assumption allows us to assume that the window has a downward acceleration of 9.8 meters per second squared due to gravity. Let's start by defining our coordinate system. So I'm going to choose the upward direction to be the positive y direction. Of course, you can have downward as positive. That's totally arbitrary as long as you stay consistent. The next thing I'm going to fill in is that about halfway up the building where the window starts to fall is 370 feet. The total height of the building is 790 feet. And then I'm going to put the ground level to be a position of y equals 0. Put feet. Now that we have our coordinate system defined, our next step is to draw our motion diagram. So this window we can assume is starting from rest, where it somehow becomes dislodged and then it goes into free fall. So putting our dot at the initial position, it starts from rest, and then we know from free fall it's going to have an acceleration downward. So its acceleration due to gravity is going to be in the same direction as its velocity. So the window is going to be speeding up as it goes down. So on the motion diagram, we expect the spacing of the dots to increase as we move further down in position. We can label the information on our motion diagram now. So the initial position of the window is equal to 370 feet. The initial velocity, we said we were going to assume that it starts from rest at 0 meters per second. The final position is when it's going to be hitting the ground. So its final position, YF, is equal to 0 feet. And then we want to know what the speed is just before hitting the ground. So we don't know its final velocity. Spanning the entire motion, we're not given any information about time, but we are given information about that the window's in free fall, which means its acceleration will be negative 9.8 meters per second squared. And then time is a question mark at this point. So filling in the rest of the first part of the problem-solving framework, we are asked to determine the time that it takes for the window to fall. So t, and we expect a positive time in units of seconds. And then the other thing is we're looking for the speed of the window just before hitting the ground. So we want the magnitude of the final velocity. And so we would expect that to be a positive value and that to be in units of meters per second. Now just to highlight the point, the final velocity, it's moving downwards and the direction up is positive, so we expect to get a negative velocity. But since the question is asking for speed, when you take the magnitude, you're only going to get positive values. So let's now plan our solution. We have two variables that we're looking for, time and the final velocity. So we're going to need two equations to be able to solve for that. So I'm going to start by solving for time. So I'm going to use the kinematics equation where it's position as a function of time. So that is y is equal to y naught plus v naught y multiplied by time plus 1/2 the acceleration in the y direction multiplied by the time squared. So we know the final and initial positions. We know the initial velocity. We're solving for time. We know the acceleration in the y direction. And again, we're looking for time. So we have one equation and one unknown in that equation, so we can solve for time. So after we solve for time, we can use the kinematics equation that's a velocity as a function of time to be able to solve for the final velocity and get the speed of the window. So that equation is Vy, where the final velocity in the y direction is equal to the initial velocity in the y direction plus the acceleration in the y direction multiplied by time. We're solving for the final velocity. We know the initial velocity, we know the acceleration, and we would have found the time from the first equation. There is also an alternate approach that you could have taken to solve this problem, where you started off by solving for the final velocity, and then went on to solve for time using the second equation. So each approaches are equally valid. It just depends on which quantity you wanted to solve for first, the velocity or for time. I have all the algebra worked out. The first step that I did was to convert the initial height from feet into meters. Of course, you could have kept everything in terms of feet, but you would have had to have converted the acceleration due to gravity in terms of feet per second squared. Both are equally valid. So after converting, I found using the first kinematics equation, I found a time of 4.8 seconds for the window to reach the ground after falling. After that, you can use that time in our second kinematics equation that we wrote down and find a final velocity of negative 47 meters per second right before the window hits the ground. Ultimately, we're asked to find the speed, so we need to take the magnitude of the final velocity, which is our final result of 47 meters per second. So to check everything, we solved for both quantities that we were asked to. The signs are both positive as expected. The units are good with meters per second for speed and seconds for time. And the magnitude of 47 meters per second is roughly 100 miles an hour. And so for skydivers in freefall, they're going a little over 100 miles an hour, so this seems like a reasonable result.